Here's problem number 3. 2 moles of an ideal monatomic gas going through the following thermodynamic process. This one, you'll notice, makes a complete cycle. It starts at A, goes to B, goes to C, goes back to A. Makes a complete cycle. And this is very typical of our engines, our refrigerators, our heat pumps, things like that. They go through a cycle and then they start over again. So what are we doing here? We're given some information, pressures, temperatures. We're given a relationship here that the volume at B is twice the volume at A or C. So we know a few things. Let's fill in what we know and then see if we can solve the puzzle, fill in the missing pieces. So first thing we know is the pressure at A. Eight times 10 to the 5th pascals. The temperature, 400 Kelvin. Make sure it's in Kelvin. The temperature at B, 300 Kelvin. So we know 2 out of the 3 things for A, so we can fill in, because we know the number of moles, we can fill that in. Oh, but before I go on, we know one other thing about this. This is this curved line between A and B. There's something special about that, where it's given that it's an adiabat. That's an adiabatic process going from A to B, which means that no heat flows into or out of our system along that path. So that's another important thing you want to note, but we'll get there in a moment. So we're going to find the volume at A. nRT over P. 2 moles, 8.31 joules per mole Kelvin, 400 Kelvin, all over 8 times 10 to the 5th pascals. And I got 8.3 times 10 to the minus 3 cubic meters. Let's look at our PV diagram. Going from C to A is a constant volume process. So the volume at C and the volume at A are the same. I'm going to go ahead and put that in here. 8.3 times 10 to the negative 3 meters cubed. Okay, and I know the volume at B is twice the volume at A or C, so I can fill that in, right? There's a relationship here between the volumes, and this is going to be 1.66 times 10 to the minus 2 cubic meters. Now I can find the pressure at B. And what was the temperature at B? 300 K. And the volume at B, 1.66 times 10 to the minus 2. And I get 3 times 10 to the 5th pascals. And I know the pressure at C and the pressure at B are the same. That's a constant pressure process going from B to C. And now I can use my ideal gas law to solve for the temperature at C. And what did I get? Pressure was 3 times 10 to the 5th pascals. The volume, 8.3 times 10 to the minus 3 meters cubed. 2 moles, 8.31 joules per mole Kelvin. And I get 150 Kelvin. So once I know the temperature at each of these states, I can go and find my internal energy, because this is an ideal monatomic gas. So what do I get? I'll just fill them in. I get a $99.72 joules, 74.79, and 37.40. Okay, so I've got my table filled in for the states. Now I want to look at the processes. Now I don't just have one process, I have 3, right? Going from A to B, going from B to C, and going from C back to A. So I want to fill in what I know here. And one thing I know, let me look at these processes real quickly. Going from A to B, that's a special process, an adiabatic process. What do we know about that? No heat flows into or out of the system during that process. So I'm going to go and put in, from A to B, Q equals 0. What else can I look at this chart and see right off the bat? One other thing. Going from C to A, the volume does not change. If the volume doesn't change, what's the work done under that curve? It's 0. No work is done if the volume doesn't change. So from C to A, the work done is 0. Okay, those are the 2 that jumped out at me. Now let me go back and fill in what I know. I can do all my delta U's. Remember, delta U is final minus initial. All right, so delta U A to B is UB minus UA. Negative 24.93 joules. Delta U, B to C, UC minus UB, negative 37.40 joules. And delta U from C to A is the energy at A minus the energy at C, and this is positive 62.32. Let me write those in. One thing that's interesting here, if you add those up, what do you get? We should get 0. Why do we get 0? We started at point A. We went through some cycle. Where did we end up at the end of the cycle? Back at point A. So we started and ended at the same temperature, because if we start at A and we end at A, we have to be back at the temperature, right, of A. A has a specific temperature. And what does U depend on? It depends on the temperature. So if you start and end at the same temperature, delta U for that process is going to be 0, right? You're going to be at the same internal energy at the beginning as you are at the end. So anytime you go through a cycle that's a closed cycle like this, a complete cycle, and you start and end at the same place, your delta U for that entire cycle is going to be 0. So if we add these up, we should get 0. I rounded off a little bit, so I'm off by 1 joule, it looks like. But you can see that, that's what it should be. Okay, the next thing we want to do, find the work done. And what can we do here? Well, we can find the work done from B to C. So let's do that, because that is a constant pressure process. So I'll write it in here in red. The work done from B to C is that area right there. P delta V. So it's the pressure at B or C, it's the same, 3 times 10 to the 5th pascals. And it's the final volume, that would be VC. Minus the initial volume, so this is going to give us a negative value. Why is it negative? Because the volume's getting smaller, right? The gas is being compressed. The piston is doing work on the gas, or the gas is doing negative work on the piston, however you want to think of it. Now, we know 2 out of 3 things. Here, 2 out of 3, here, 2 out of 3. So we can solve for the missing one using our first law of thermodynamics. So we're going to find and this one is positive 2493. This one is negative 8720 joules. And this one is positive 6232 joules. Okay, so in going from A to B, the system, the gas, did positive work. And if it does positive work, we would expect the energy of our system to go down, delta U to be negative. it depends on what Q is. In this case, Q was 0. So this makes perfect sense. Q is 0 if work is positive, then we've got a 0 minus a positive number, so we get a negative delta U. So that makes sense. Those numbers, I think, look good. How about going from B to C? The gas is compressed. Work has to be negative. We got a negative value. And it just depends now what happens to other things. If, in this case, typically when you compress a gas, it heats up. In order to keep the pressure constant, we had to remove heat because we're compressing the gas and the pressure stays the same, which means the gas has to be moving slower at the end than what it started with. So we had to pull a lot of heat out. As the gas compressed, we had to pull a lot of heat out in order to keep the pressure the same. So Q has to be a big negative number. And then because it's more than W, we have to kind of look at the numbers we got. We got a Q that was bigger than W, so therefore delta U has to be negative. And then we can go back and look at our temperatures and make sure that makes sense from that aspect also. If the temperature went down, delta U is negative. And then C to A, no work is done. If no work is done, how does the pressure go up? Well, we dump heat in, right? Get the molecules moving faster, they bang on the wall harder, the pressure goes up. So if no work is done, why does the pressure go up? Because we put heat in. Positive Q. If Q is positive and this is 0, then that has to be positive also. So it's a good idea just to think about that a little bit. 3 processes becoming a little more detailed with each step. What I want to do now is sort of show you this isn't the end. This is just having this information is nice, but that's not really the final result that we're looking for. So let me point that out to you.